We'll just wait couple of more minutes for people to join. We'll start. Welcome to problem solving session on thermodynamics. This is the first week, and this week we'll see on the basics on thermodynamics. We'll see what is system, system boundary, what is surrounding, what does it mean by a process, and do some simple calculations on pressures, and see a simple system, how to do apply control volume, and see what type of system it is. So we'll see some problems related to those. And so to start with, thermodynamics is basically anything energy. Thermo means heat, dynamics is in motion. So anything energy in motion, you can say. So we'll use this to study system, model system. So we can find applications, variety of applications, taking from your normal day-to-day life engines. You can apply the principles of thermodynamics. You can apply it anywhere and can try to model it and try to study the system. So starting with studying the system, so what does the system means? So the system, say whatever we want to study, whatever we want, say anything. If you staring at your laptop, so your laptop you want to study this, so this is your system. So that basically defines what is the point you want to study. So the shape or volume of the cylinder which is being analyzed, it's a basic definition which they have given. So not necessarily be a constant one, can be a variable one. You can say in the space, you can try to put up a consider the space. It can be not constant, it can vary. So that what basically means. It's not be a fixed space, it can be a variable space. So anything which you want to study is called a system, and the anything outside of this, you can call that as a surrounding. And so if you have system, anything out of which is out of your study, which you don't want to focus, you don't want to consider, so that is your surrounding. And the region which differentiates these two, so you have a system which you want, which is your study part, and one which is which you are not considering, that is your surrounding, and the one which is distinguishing these two, it's called the boundary. So now a system can be of three types. You can say one is of closed type, basically two types. One is in special case, so it's called a closed system or an open system. So you have a closed system, there you don't have any mass transfer happening. So in that case, it's a closed system. You have an open system. In case you can have a mass transfer, you can have anything, any fluid or any mass which can enter or go out. It's called an open system. So a special case of system in this is an isolated system. So isolated system is one where you don't have any mass transfer as well as there is no energy transfer. So that is called an isolated system. So in our best example of isolated system is our universe. So assume our whole universe is an isolated system. We don't have any everything which is there, it is inside our universe. Nothing is going out, and everything, because everything is bounded inside. Energy, there is no energy interaction with anything else, and there is no mass transfer. So it itself is an isolated system. So that is an example of an isolated system. And as I said, the other thing is our closed system and an open system. The open system is also called as a control volume. In this case, you are fixing a volume and you are focusing on those. So hence it's called a control volume. So because this volume is fixed, there can be any mass which is entering and which can go out. So just a recap of the previous week. We'll see just the recap and we'll start with numericals. Then now we have seen a system and we have seen surrounding and we have seen what type of system it is. So now how will you define a system? You say how will you just like each system has a name. Your system also has to pinpoint this that or you say so you if you ask you say a person you define ask a person where are you or you define a state of a person, so he'll say I'm at this location or pinpoint, so you that is kind of a state. So how do you define a system? So similarly a system is also defined by a state. A state is a condition which is defined by some properties of those system. So what are these properties? So these properties are macroscopic characteristics of the system. So like a mass of the system or the volume of the system or pressure, temperature. These are all properties which can be used to define the system. And now as we have seen property, so any system can go through a process or a change in property. So it will go through a definite change in property. So this changing property is called as the process. So from one state it goes to another state. So this change in state is defined by a process. So in this process, a process can be any can be reversible, or we call it reversible or a quasi-static process. We assume it to be a reversible. In reversible in sense, from state 1 to state 2, when the system has reached, when you go back from state 2 to state 1, everything goes back to the previous case. So that is called a reversible. Even a surrounding and the system which you are considering, both has to go back to what it was there in the previous case. So it's called a reversible process. Ideally speaking, in the day-to-day life which you see, it will not be a reversible process. It will be irreversible. It's called an irreversible process. So we'll all see how to calculate those in the coming weeks. So the process, we have seen a process. Now when do you say a system is in a steady state? So you say a steady state when your system doesn't change with time. So your property, if you take, it will not change with time, it will not vary with time. So in that case you will say that your system is in steady state. Now these properties can be of two types, can be of extensive type and second is of an intensive type. So extensive type is a property which is dependent on mass, you say, or the shape or volume of the system. So for example, if you take 100 kg of say water and you split it into two, so now each two system will have 50 kgs and 50 kgs. The volume occupied will also be different. So this pressure and volume, now these are extensive properties because these are dependent on the shape and volume of system. But if you take the density of the water which it was there previously at 100 kg, it will be same, and you split it into half. Now also the density of the water will remain same. It will not vary with its size or the mass or say. So this is independent of mass, you can say. So this density, for example, in this case, it's independent. So even another example which you can give is say your atmospheric pressure. You know, your atmospheric pressure is at 1 bar. So now you close your room. So you cannot say that my pressure inside the room is any different from the atmospheric pressure. So your pressure is still the same. So this pressure is also again goes to an intensive property. So another example of intensive property is your temperature. So again take an example of this temperature. If you see, you have as I told previously, water. If you again go with an example, you boil the water, you have boiled it, so your water is at 100 degrees Celsius, for example. So now you split that water into two. Do you think the temperature will change? Both the water will be at the same temperature. So again, then example is it's an intensive property. So generally speaking, if you don't know any property, can try to visualize this in this case, can try to split it and see if the property will change. So if it doesn't change, it's an intensive property. If it changes, it's an extensive property. And any extensive property can be changed to intensive property dividing by a mass. So we'll see. We'll be using those in the coming weeks. Just to heads up, you can find an intensive property from an extensive property by dividing mass. So starting, these are all just a simple match the following question. So these are all we discussed in the previous. So that, and you have to just match the followings. I'll just give you 5 minutes. You can type it out in the chat box. So it can be you can also try a small this thing. If you make mistakes, you can ask me, and we can discuss that out. You can chat the answers in the chat box. So it will be like you can test it out yourself. Okay, so starting is the boundary. So the boundary, as we have seen, it's the one which distinguishes the system and
iPhone.
sorry.
iPhone, sir, iPhone.
Yeah. So the answer is I. Distinguishes the system from its surrounding. The answer for the next one, the closed system. So if you see closed system, closed system is anything you do doesn't have any interaction with mass, but you can have energy transfer. You can have a transfer in terms of heat and work, but you will not have any mass transfer. So the answer is G, a fixed quantity of matter. So for 2 is closed system is a G, a fixed quantity of matter. Now so a closed system, you have a fixed mass. You don't have any mass flow or in. So whatever mass which you have inside will be same. There will be no change in your matter. So you will just have interaction with heat or work. So for 2 it's G. So the next one is the control volume. So again, control volume can also be told can be termed as open system. So for this control volume, the answer is a region of space through which mass may flow. So option B. So now you are fixing a volume. So you are assuming space. So in that case, you can have any flow of mass or energy. So that's what open system means. So or a control volume. You are fixing up a volume. So control volume. So answer is B.
Excuse me, sir.
Yeah.
Sir, there is any difference between closed system and control volume, sir?
Yeah, closed system you don't have any interaction of mass. There is no flow of mass through it. In control volume you can have a mass transfer.
Okay, sir.
Yeah, we'll see some examples. It will be even more clear. If you are not clear with that, you can ask again. Okay. So the next is extensive property, as we have already seen. So extensive property, a property whose value for an overall system is the sum of its value for the parts into which the system is divided. So as I previously gave an example of water, you divide it into 50 and 50. So you add it up, you get 100 kg again, the initial one. So that's what E means, a property whose value for an overall system is the sum of its value for the parts into which the system is divided. So 4 is E. Fifth is intensive property. So if you see intensive property, which is independent of mass, so or independent of size, you can say size or extent. So H, the property whose value is independent of the size or extent of a system and may vary from place to place within the system at any moment. So what does this mean? It's basically says that its value is independent of the size, but it may vary in the system. It may vary for the moment. So what we take as the intensive property, say for temperature or pressure or density, is that is the average value of the system. But inside the system, there may be some change. It will not be very much, but there will be some change. So that's what it means. So intensive property is option H. 6 is process. So process is option D, a transformation from one state to another. So we saw process change of state from one to state. How it occurs is called as process. 7, a property. So property is option J, a macroscopic characteristic of a system to which a numerical value can be assigned at a given time without knowledge of the previous behavior of the system. So that is property, the definition of property. So what it means is the value assigned at any point, there is a numerical value which can be assigned to that property, and it doesn't depend on its previous value. So it doesn't depend on its history, how it went and previously which state it was there. It doesn't require any of those. At given state, it will have a certain numerical value. So that's what is property. So that is corresponding to J. So next is state.
Is it A, sir?
Sorry, just checking. The condition of a system as described by its property, that is state. Answer is A, correct. And the next, surrounding. So surrounding, as we all know, so here everything external to the system.
F1.
So everything external to the system is what you study. So everything external to the system is your surrounding, and then finally system is whatever is studied.
C.
So C.
C1, sir.
Yeah, correct. C. So now we have seen, we'll see in brief what we can say. I have listed out some examples of this closed and open system. So if you see the first one, we have a fixed system, and outer box with the cross hatches specifies an insulation. So insulation in this case means there is no heat transfer can happen. So there is no mass transfer which is happening, and this is insulated, and there is no work which is happening. So the system is a closed one. It's adiabatic. Adiabatic in sense there is no heat transfer. If there is no heat transfer, we call it adiabatic, and there is no work transfer. So if you see any closed insulated fixed vessel, it's your closed system, you can say, or isolated system. For this case, this will be an isolated system. First one will be an isolated system, because this is closed. There is no mass transfer, there is no heat transfer, and there is no work transfer. So there is no transfer between the system and its surrounding. So this is an isolated system. So next one, you have similarly your system which is closed. There is no mass transfer happening, but there is a heat transfer. There is no insulation. In the previous case, it was insulated. Now it's not insulated. So there can be heat transfer, but still there is no work transfer which is being happening. Before okay, I'll just define you what heat and work is. So for heat, if there is energy transfer between a temperature difference That form of energy is called heat. So we basically know what heat is. Anything you energy in form to raise a temperature, we call it heat. And you have work. So work in thermodynamics is defined as any form of work in which you raise mass to a certain height. It's called work. It can be of any form, but ultimately that work should it can be converted into raising a mass to some extent. So that is called work. So if you are able to do that, then that kind of energy is work. So here you have a system, there is a heat transfer, there is no mass transfer, and this is a closed system. So it's a closed, it's a non-adiabatic, so there is a heat transfer, and there is no without work. So it's still again a closed system. This is not an isolated system, but it's a closed system. Then again another example of a closed system, we have a system. In this case again it's an insulated, so this is a piston arrangement. There is no mass transfer happening because there is fixed volume of fluid which is there inside, and this is pushing the piston. So if because of this there will be work done which will be happening. So this is a closed system, there is no mass transfer happening, and there is no heat transfer, but there is a work transfer. So again, so in this case it will be a closed system, but there's a instead of work heat, it will work. So it's a closed system. So this is a change of the previous one. In this case you have removed that insulation, so now you have both heat transfer and work transfer. So now this is still an closed system. This is different types of closed system, so examples of closed system. So you have fixed mass, you have heat transfer happening, and you have work transfer happening. So closed system. And now you take an example of a open system. You have an insulated tube, you have there is no heat, so insulation, so there is no heat transfer, and the mass is just flowing, so there is no work transfer. So as this is mass is flowing, it's an open system, open adiabatic without work. So this is an example, is an insulated tube. So this is an open system. So again down, if you see, there is a mass transfer. There are two tubes, so you can say two tubes which are joined together. So in both of which mass is flowing, and you can assume that both are at different temperatures. So because of that, the heat is transferred between the two. So this is an example of a heat exchanger. You see outside is insulated because heat transfer is happening only between the two fluids. So this is still an example of an open system because mass is coming in and going out. So again example in the previous, because of insulation, it's without insulation, it's again an open system, but you are losing heat to the ambient. So these are just different types of open system and giving you examples. So if you see a reciprocating pump, so this is an example of a reciprocating pump. You see there are two valves, saying mass is coming in through the valve, it will come in and then go out. So in the process the piston is moved. It's just like similar to your engine piston pump, engine piston. So similar to that, you have a suction and a discharge. So fluid comes in and then goes out. So this is still an open system because this is insulated, it's an adiabatic, but there is a work transfer. And again the next example is open, but it's non-adiabatic because there is a heat transfer happening. You can say the second one is a piston, compressor, or engine. As I said, engine, you see a engine, if you touch it will be how hot, you can feel. You cannot touch it, will be a higher temperature. So it will be hot. So there is some heat transfer happening between the engine and the surrounding, because engine it will be a higher temperature, so it will lose some of the heat to the surrounding. So that is a heat transfer. And your mass is transfer is your fuel which is going in, or air which is taken in, and that is your inlet, and your mass outlet is the exhaust. After burning this thing, the exhaust which is coming out, that is your mass which is going out, and the work transfer is just what the work which is done by the engine to move the car. So that is the example here. So the system of the, we are just considering that piston arrangement, piston and cylinder arrangement. So this is an open system. Similarly, turbine system. So the turbine is something you have it's just call it an expander. You can, a simple example look like a fan. You have, but the shape of the this thing will be different. So fluid will flow, rotate it, and it will expand on the process. So in that case also we'll have a mass transfer. So you have an open, in this case it is insulated, so it's an adiabatic, and this is and it will do an because it's expanding, this will do some work. So turbine, so it's an open system, and similarly this is a compressor, so it's the other way around. It's just the same, but it's it's in the other way around. It operates differently. You give in work and it will transfer fluid. So is again an example. You see there is a mass transfer happening, there is heat transfer. So again an example of open system. So it's all, now we'll go back to simple this thing. So you have a cup of tea, so it's hot, you poured a cup of tea, you kept it. What do you think? In this case you have heat transfer happening, and there's a mass transfer also happening, because tea is hot, you'll evaporate some, this thing will go into air, so there will be mass transfer which is also happening. So the first case is an open system. The same, this thing, your tea, now instead of opening keeping it open, you close it with the lid. So now there is no mass transfer, but still from the cup it will lose heat to the surrounding. So on the same open system, now we have converted it to a closed system. Now there is no mass transfer happening. Now I say, no, I want to drink it hot, why will I lose it? You pour it in a thermos flask, so now this is insulated, so you have made that to an isolated system. So you can see examples of the systems are all around us. So moving on, so we saw what an extensive properties and what are intensive properties are. So here there are some lists of properties which are listed in each example, and we need to find out a list which contains only the intensive properties. So first one is the volume, temperature and pressure. B, specific volume, mass, volume. C, pressure, temperature, specific volume. D, mass, temperature and pressure. So what do you think the answer will be? I listed out everything as the previous example. So the answer is C, pressure, temperature and specific volume. So volume is a extensive property, but specific volume is an intensive property. Specific volume is nothing but volume divided by mass, or you can say 1 by density. It's called specific volume. So that is an intensive property. So the answer is option C, pressure, temperature and specific volume. So anything with the name specific before the property, you can assume straight away that is an intensive property. So next we have an example here. It says a 1 meter cube container, which is shown in the figure, is filled with 0.12 meter cube of granite, 0.15 meter cube of sand and 0.2 meter cube of liquid, which is at 25 degrees Celsius, 25 degrees Celsius water, and the rest of the volume is 0.53 meter cube of air. So the density of air is given, and the density of the granite, sand and water is also given. So in this case we are asked to find out the overall specific volume and the density of the container, including all air and this thing. So how will we find this? So we have from the definition of specific volume is V by M. So as I told, or we can say 1 by rho. So rho will be mass by volume. So they have asked to find out specific volume and density. You can find either of it, and you can find the other. So for that we need to find out the mass and the volume. So we know the volume from the example previously. He has already listed out. It's 1 meter cube. So we know the total volume, which is 1 meter cube. And now what we'll do is, we know individual volume of each of the components, and we know the individual densities. So using that we can find out the mass of each of the components. So for example, for this mass of granite, so mass of granite is nothing but the density of granite into volume of the granite. So it's a simple formula. Rho is m by v, so you take v to the other side, you can find out mass. So mass is density into volume. So we know density is 2750 kg per meter cube, which is already given, and 0.12 meter cube is occupied by granite. So that will give me 330 kgs. And then mass of sand. So mass of sand is density of sand into volume of sand again. So density of sand is given as 1500 kg per meter cube and 0.15 meter cube of sand. So it will come out to be 225. Similarly, mass of water, so density into volume of water. So here the density is given as 997 for 25 degrees Celsius water. So equal into 0.2 meter cube. So say similarly 199.4, and similarly for air 1.15 into 0.53, it will come out to be 0.61 kgs. So this will come out to be V is the total volume divided by specific volume is total volume divided by total mass, which will come out to be 1 by 755 equal to 0.001325 meter cube per kg. You can inverse this to find out density, or you can use the mass by volume again, and density will come out to be 755 kg per meter cube. But in this question they said they didn't specify what, so we assumed all total including air. But in simple, the air doesn't form a mixture with the granite and sand, so air will be separated. So basically speaking, you should not consider air, but in this case they asked for overall, so we have already also calculated using it. So if you see that mass of air is very less, 0.61 kgs compared to the others, so it will not affect much, but okay. So the next one is to find out what is the pressure at the bottom of a 7.5 meter tall storage tank of fluid at 25 degrees Celsius. So you have a storage tank, a circular tank, which is given here. So this is example. So you have this you are saying the pressure at the bottom of this 7.5 meter tall storage tank. So H is 7.5 meter tall. Assume that the fluid is gasoline with atmospheric pressure 101 kilopascal on the top surface. So they are asking to repeat the question for a liquid refrigerant R134A, and the top surface pressure is 1 megapascal. So the gasoline density is given 750 kg per meter cube, and for 134A the density is given as 1206 kg per meter cube. So again, also second part, now discuss the type of system when the fluid filled is liquid nitrogen, liquid natural gas LNG, which is at minus 160 degrees Celsius. So you can try this out. I think it's a simple example. You can try this out and you can type your answers in the message box. I'll wait for 2 minutes. Okay. You can try this out. Simple example. You know G you know the top pressures, you know densities. So this is how you solve. So you have a pressure difference due to gravity. So you will have what that is rho gh. So that is the pressure exerted on the bottom of the fluid on the bottom. So the pressure is exerted due to gravity. So rho gh. So that you know density, you know acceleration due to gravity g, and we also know the height of the tank. So the total pressure will be the top pressure, the pressure at the top, plus the pressure occurring because of this gravity. So this will be for gasoline, the pressure difference will be rho gh. So rho is 750 kg per meter cube. Your density is 750 kg per meter cube, and your acceleration to gravity is 9.807 into height of the tank, which is given as 7.5 meter tall. So into 7.5. So it will come out to be 55,164 Pascal. So you can divide by 1000 to make it kilopascal, and we know the top pressure is 101 kilopascal. So 101 plus 55.164 will give me 156.2 kilopascal. So this is the pressure exerted at the bottom of the tank, you can say, for if it's filled with gasoline. And second one is for R134A. So a similar approach. So you have pressure difference, you can calculate by rho gh. It will come out to be so rho gh is, if you see, it's nothing but you can see pressure exerted by the weight of the water above. So that's what ultimately, if you see your weight, you can calculate by mg, mass into gravity. So that you divide by area. So you can area, so you multiply by height and height, so you will get volume down. So m by v is rho, so rho gh, you will get rho gh. So that is you can say pressure is force by area, so mg by a. So it's nothing but the pressure exerted due to the weight of the fluid which is above the part which you are considering. So rho gh, so rho is 1206 for R134A, so g is 9.807, and h is 7.5 meters, same. So assuming the same tank, so it will come out to be 88,704 Pascal. So that is 88.704 kilopascal. So that and we have given this top surface pressure is 1 megapascal for 134A. So 1 megapascal is 1000 kilopascals, or 10 power 6 pascals. So 1000 kilopascal plus 88.704 pascal, so it will come out to be 1089 kilopascal. So you are rounded off 1089 kilopascal. So the second part of the question was to discuss the type of system. So you see now this is liquid natural gas LNG, which is at minus 160, liquefied natural gas. So in ideally speaking, this should will be an insulated vessel, and this being a closed vessel should be an isolated system. So but practically speaking, you will always have heat transfer happening. So in that case, it will be an closed system. So moving on, we have a piston cylinder with a cross sectional area of 0.01 meter square. There's a piston mass of 100 kg resting on the stops. So we have this piston cylinder arrangement. We have, this is the piston stop, piston with the piston stop given. So this the top of the piston is there. The weight of the piston is 100 kg. So this is resting on the stops and with an outside atmospheric pressure of 100 kilopascal. So you have outside pressure of 100 kilopascal. So what should be the water pressure be so that it can lift the piston? So you can try this example. So I'll wait for another 2-3 minutes. You can try. I'll give you a hint. You have to do a force balance. Or you can do a pressure balance also. Either way you are comfortable with. So if you see, we consider this example. You have piston cylinder and water. So water is exerting a pressure. So if the pressure is above certain value, it will lift the piston. So because this thing to lift, you need a force. So that will be P by A. So you need to find out that pressure to lift that piston. And outside, if you see, you have the force which are acting is the pressure which is exerted by the atmosphere, which is 100 kilopascal, and then the weight of the piston which is being acted on the water. So these two are acting on the outside. From inside you have water which is exerting pressure on the piston. So you have to just balance this and you can find out the pressure exerted by water, or which should be greater than for that piston to move. So as I said, it's simple force balance. So what we do, we know pressure is force by area, force per unit area. So force will be pressure into the area on which it is acting. So in this case, area is the piston area, surface area of the piston on the one side. So P is the pressure acting on the inside, the water which is exerting pressure on the piston. So that is P into the area of the cross section area of the piston. So that is the area in which the water is exerting the pressure. So force will be P into A. Similarly, on the other side, if you see what is exerting on the water, you have mg. Mg is the mass of the piston, or the weight of the piston which is acting on the water. So mass into acceleration to gravity, mg, plus you have P naught into A. P naught is the atmospheric pressure, and similarly your area will be same, either from the bottom or the top, your area is same. So again, area of the piston into the atmospheric pressure, so that will exert a force on the piston, so P naught A. So now we can just divide this whole thing by area, so you can find out the pressure here. So pressure P is mg into mg divided by area plus P naught, just rearranging. So we know P naught, which is 100 kilopascal, so atmospheric pressure, plus new mass is given as 100 into G is given as 9.807 divided by area is they have given 0.01 meter square. Sorry, I made a mistake here, it's 0.01. I'll change that into 1000, because mg by A, which will give you in Pascal. To convert it into kilopascal, I have divided it by 1000. So kilopascal, which will come out to be 98.07. So this is 0.01, it's not 001. So 100 plus 98.017 will come out to be 198.07 kilopascal. So if your pressure is 198.07 kilopascal, it will be in equilibrium, it will not move. But if it exceeds 198.07, the piston will start moving. So here we are assuming it's a frictionless piston. So in that case, it will be this pressure. If friction, you consider friction, then pressure may go up. So here, the assumption here made is that your piston is frictionless. There is no friction acting on the piston cylinder and the piston. So this is the pressure. So the next question is, you have a wind turbine and an electric generator. It's mounted at a top of a tower. So at a tower you have a wind turbine and an electric generator which is mounted. So as the wind blows steadily across the turbine blades, electricity is generated, and the electrical you have electricity which is coming out. So considering only the first part of the question is considering only the wind turbine, electrical generator as a system, identify location on the system boundary where the system interacts with the surrounding. So we have to find out the system boundary where this system will interact with the surrounding, and describe changes occurring within the system with time. Then the time put out generator is fed to a storage battery, and so you have wind generator with the turbine, and then that is connected to a storage battery where electricity is passed and it's stored in the storage battery. So now the second part of the question is repeat for the same system that includes only the storage battery. So previously, now we are considering only the wind turbine and the electrical generator. So this is the first part of the question, and second part we are considering only the storage battery. So what will happen in that case? So that's what has been asked. So if you see in this case, there is a wind turbine. So it's an example of a windmill which is given, and at the top you have the blades, and you will have this thing, wind turbine and electric generator, which is said the system as a combined system, to be mounted at the top here where the air is flowing. So now we are considering this whole part as a system in the first case. So in the first case, if you see, you need air flow to happen to rotate this turbine, or else this will be steady. There will be if there is no movement of air, so the blade will not rotate, and there will be no electrical being generated. So this will be in that case you can assume that to be a closed system. But as this thing to generate electricity, there will be a mass of air which is coming in and going out. So there will be air flow. Because of this air flow, this thing will rotate. So this will be an open system. And other interaction which is happening is because of the air flow, the blades will rotate, and the generator will generate some electricity. So this electricity is passed through the wires. So these wires, and it's going to the storage battery. So there is another interaction happening through the wires. There is a electric energy which is being sent out. So this is an open system. So you can say the wind turbine is studied as a control volume with air flowing across the boundary. So another interaction which is happening is the electric current passing through the wires. So you can say another if you want to stay, you can say that this is a steady can say steady state, because when the wind, we assume that wind is flowing at a constant velocity and it's not varying, so steady wind. So in that case, this operation will be steady operation. So it will be a because the flow is because of the air coming in, your blade rotates, so the velocity or the rotation speed of the rotation depends upon the velocity. So because this thing is constant, your air which is coming in is at constant velocity, your electricity will also be constant, so everything will not vary with time. So you can assume, in that case, you can assume this to be a steady state system. The second part of the question asked you to consider only the storage battery. So if you consider only the storage battery, so in that case, the electricity which is generated from the wind turbine is passed through the wires and it goes and it's stored in the storage battery. So there is an interaction happening between the because of the wires, there is a energy which is coming in, and then because batteries, what happens, you charge and discharge. In the process, there will be some heat which is generated because of the chemical reaction which is happening inside the battery. So that will be heat, will be rejected to the ambient. So there will be some thermal interaction. So that is another part of the interaction which can happen. So these are the two. If you see this process, is it a steady process? You cannot say it's a steady process, because the reaction or the chemical reaction which is happening inside depends upon, initially it will be fully discharged, but as the time progresses, because of the electricity which is coming in, the battery will start charging. So it's varying with respect to time. So this is not a steady state process. So that's what can infer from the problem. So moving on, I think this is a final problem. You can ask questions. Okay, you have one more. Okay, you have if you have any questions, you can ask anything about the first week, or you have any questions on the examples, you can ask, or you have any general doubt on the week's course, what you have learned throughout the first week, you can ask that too. Even if you have a query, you can use a message box as well to ask a question. Okay, so the problem goes like the driver of a car of a total mass m driving at the speed c must slow down to stop over a distance l. So the car is driven down a hill with a slope corresponding to angle alpha. So you have a slope, so the angle is alpha, and initially the car which is at the top has a velocity c, and you want to for the car to stop at the distance l. So you are applying brakes. When your velocity is t at the top, you apply brakes and it has to come to stop in length l, and the slope of that road is at alpha. So now they say the internal energy of the car at rest after cooling is the same as the initial state. So that is the assumption they are making. The air drag is neglected and there is no slip on the wheels of the road. So the wheels are not slipping, there is no air drag. So these are assumptions which are they making. So the knowns are, we have a distance, the L is 100 meters, and we know that tan alpha is 0.07. They are saying the initial speed of the car is 72 km per hour and total mass of the car is 1000 kgs, and the acceleration due to gravity is 9.81 meters per second square. So we need to find out what is the change in the total internal energy of the car and the heat. So internal energy is change, just we have to find out how much work which is being done from point 1 to 2. So that's what we need to find out. So we do energy balance to find out this. So work is nothing but, initially the car was at some energy, and at this point it will be at some other energy. So the difference between an energy is what will be the difference in the internal energy of the car. So initially it had some velocity c. So because of that it will process some kinetic energy mv square, and this is at a height h. We need to find out that height. So that will be L sine alpha. You see the slope is alpha, and it has to go distance L. So the total height which it has come down will be L sine alpha. So that is the decrease in potential energy which is coming. So at the final, when the car comes to rest, so its energy is 0, and the initial energy which is processed is the kinetic energy and the potential energy. So minus mv square by 2 minus mgh. So that is the both the energies which it had previously. So we know h is L sine alpha, and we can find alpha using the known tan inverse 0.07. So it will come out to be 4 degrees. So on substituting this, and velocity is given as 72 kilometers per hour, we are converting it to meters per second. So it will come out to be 20 meters per second. So we substitute this, and the change in internal energy will come out to be minus 268.7 kilojoule. So this is minus because initially it had some energy, so now you brought that to rest. So that's why it is in minus, because initially it had some energy which was there. Now you are bringing it forcefully to a stop, so now it has lost that amount of energy, so hence this is in negative. Similarly, the second part of the question was calculate the heat generated during the braking. So this is the energy which the car lost while coming to the stop, right? Where will this energy go?
So how velocity?
Sorry?
So how velocity it in 70-20,000?
How both are equal? That's what you're asking is.
Yes.
Sorry, it's not clear. Can you repeat again?
So how velocity we got as 70-20,000 by 3,600.
Yeah. So this is 72 kilometers per hour. So kilometers, you're converting it to meters per second. So kilometer is 1000 meters. 1 kilometer is 1000 meters, right? So into 1000 divide by 1 hour is 3600 seconds. 60 into 60. So hence 72 into 1000 divided by 3600. So you can convert 72 kilometers per hour into 20 meters per second. Is this clear? This is what you asked?
Yes, sir. Yes, sir.
Okay. So using that you have calculated work. So your car possessed some amount of energy. You forcefully applied brakes and you brought it to stop. So in that process, that car has lost some energy. So it cannot. Where will the energy go? It cannot go anywhere, right? It can go to the environment. It will go to the environment. So how will it go? It will go in form of heat. So this friction brakes which you apply, it will apply friction on the wheels. Because of that, it will the energy will be dissipated in form of heat. So that will be equal to 268.7 kilojoule. So the whatever energy, internal energy you are losing in the process of braking, that is dissipated in form of heat to the environment. So hence it will be same. So I hope this is clear. So moving on, we have you can say taken a bigger type of system. We were looking at a smaller systems. We saw a teacup, we saw a tank. Now we went this thing, and we want to put up a control volume across a power plant. So this is what generally a power plant is given. So So you have multiple components. So you see this is a whole power plant. You have a chimney, so and you have a ash separator, you have coal burning, this thing, you have a steam and oil, this thing, you have pumps, you have heat exchanger, turbine, and then generator. So you have multiple this thing, but you can whole this thing you can simplify into putting a control volume to study the whole power plant as a system. You can study it simply as a system. So in this case, if you see what all is happening, main thing is this thing where energy is generated, heat is generated using coal. So there is for burning you need coal, which is going from the coal silo, which is mentioned here, and then you have air. So both you are using it to burn that, and because of that energy is generated, heat is generated, and the after burning you left out with some ash. That is where the slag is mentioned. So that is an exhaust. We are taking it out. So as a power plant, it may look very multiple components, big thing, but what is generally going in is you are having coal and air which is going in, and then you have ash which is coming out. So there is a two mass transfer which is happening, coal and air which is going in, and then ash which is coming out. And this part of the system where water is circulated inside the loop, this is inside the turbine, and it's not coming out and going in, so it is inbuilt. So in some power plants that can also happen, where you take water and you can dump water again, so that can also be a mass transfer happening there. And the other part is the chimney, where the exhaust gases are put up. So there is another mass transfer which is happening. So there, if you see, there are three mass transfer for the given this thing, which is coal, air, sorry, four total mass of coal which is going in, and then air, and then there's a slag which is going out, or the ash, and then exhaust gases. So these are the mass transfer which is happening in the power plant. And the second this thing is the power plant, so you generate some electricity. So there is a electricity which is coming out. You can consider that as an energy or work. So that is supplied through the power grid. So there is another transfer of energy which is happening. And then you have a district heating which can happen. So district heating, what it does is it's not used here, but abroad at coal, this thing you can use some of the heat which is produced this thing to heat use it for heating the houses or where cold climates are. So that is the district heating. So there in that form you are transferring some heat. So this is the overall power plant. So that can be simplified into this simple process, simple examples. You see, this is the whole box you are considering is the box which you put across this power plant. So now you are assuming this, the whole box is your power plant. So you see there is a coal coming in, and then the flue gas which is going out. Then combustion air is the air which is coming in for combustion, and there is some ash which will go out, that as well. And then this underground cable is the electrical work which I talked, so it will go out. And this is the water which is used for the district heating, which is coming in and going out. So if you see, this may look very big, but you can simplify this, and this assuming you're putting a control volume across the whole power plant, and you can simplify it into just the mass and energy balances. Now you can study the whole power plant as a simple process. You can do it for any of the components as well. So I hope this is clear, how to draw control volume, how to study that. So you see, we have put up a control volume across this thing, and we saw what all energy transfer is happening. We saw what all mass transfer is happening, and we are able to simplify the whole plant into a simple region of study. I hope this is clear. If you have any doubts, I think the examples which I have prepared for today, I have finished all. If you have any doubts, I'm open to that. You can ask any questions on this week or which was your lectures which you're seeing. If you have any doubts, you can ask those. Anyway, I'll be uploading the videos and the slides on the folders, and you can view them later. You'll get the link for those, and you can download and view those. If you don't have any queries, I think we can wind it up. If you have any queries, I'm open to that. You can ask questions. Okay, then thank you. If you don't have any queries,
Thank you, sir.
thank you.
Thank you, sir.